thank you. It's an honor and pleasure to be here and to tell you about some things that I have found amusing and entertaining. So I don't have any jokes to start off this talk, but I have to admit that this is sort of a funny talk. So I want to talk about two examples. So these symbols will be explained later. Attributions, collaborators, hypotheses will all be added in. So here's the first example. And the second example. And so this is a little bit funny because it may or may not look like these two examples belong in the same talk. But part of what this talk is about is a thread that ties these two examples together. And that's a motivic version of the, a way to view a motivic version of Thomason's homotopy limit problem. So maybe I'll start off just recalling what that is. So there's different ways to phrase this. The way that I'll work is I'll take an equivariant spectrum and very simply stated, it's, well, we consider the map on fixed points and to homotopy fixed points, and we ask how close is this to an equivalence. Okay, well, you know, this is a very general question. There's really no general answer to it. The interest is in particular examples. Oh, it's down here. There are many, many important examples. I won't give an exhaustive list. Maybe, so an example I won't really talk about, but was Thomason's motivating example, is the following. So we have a Galois extension of fields, finite Galois extension of fields. And we take a look at the algebraic K-theory of the ground field K. That maps to the algebraic K-theory of this larger field. Lands in the homotopy fixed points. So here G is the Galois group of L over K. Oh, I guess this isn't obviously of the form that I phrased it right there. I'm not going to worry about that in this talk. That's not what this talk is about. A very nice, concise explanation of why these two formulations are the same can be found, for example, in Mona Merlin's thesis. The Lichtenbaum Quillen conjectures say, well, okay, you can directly see that this map is not an equivalence. That the Lichtenbaum equivalent conjectures tell us or say that, well, if we pass to a P completion and we take high enough connected covers, we have an equivalence. So this is an equivalence on high enough connected covers after P completion. And here, of course, P should be different than the characteristic of K, and maybe I want these fields to be not too large, let's say finite VCD. And maybe I'll just say that this follows from valence and Lichtenbaum conjectures. In motivic cohomology. If you haven't heard by now, these have been resolved by Blavatsky, Rost, and friends. Another example. Well, that's phrased starting with an equivariant spectrum. Maybe our favorite equivariant spectrum is the sphere spectrum. So why not look at this map? And well, this equivariant formulation of Siegel conjectures is that this is an equivalence after completion at the augmentation ideal. And I guess in the first talk, in Haynes' talk, we already heard a little bit about a smidgen about the history of this. So the case C2, I guess that's Lin's theorem. CP, I believe this was Gunawardena. CP to the n. That was Ravenel. Product n copies of CP. This was Adams, Gunawardena, and Miller. And then finally, so this looks like a lot of fun, but then Carlson ended it and the last example that I want to mention to set the stage is, last example that I want to mention to set the stage is this example. So here, K is nice field. This is the K-theory of symmetric bilinear forms. And here we have the action given by just sending V to its dual. And, well, the solution to this homotopy limit problem, so this was Hucrish-Ormsby. This is characteristic 0 and positive characteristic. Barrick, Karoubi, Schlichting, and Ostler. This is characteristic, positive characteristic, but not equal to 2. So here the solution is this is an equivalence after 2 completion. And we should say finite VCD. Okay. So there have been several talks on motivic homotopy theory. And I'll follow in their tradition and decline to say too much about how to construct this, but I want to consider an equivariant version, so maybe I should say 1 or 2 words. So the current state of affairs is, if we're considering equivariant motivic homotopy theory, we should always assume that our representation theory is nice for G, just a finite group. What that means is that the order of the group is invertible in the global sections. It's invertible on S. So I didn't initialize this notation, so S is always going to be a Noetherian base scheme. Probably the Noetherian isn't really needed, but let's not worry about that. So what do? We start life off considering smooth G schemes over S. We enlarge this. We impose relations, and we stabilize. So, 1, this is just the Uneda embedding of that category into the category of presheets of spaces. So now that's a setting in which we can do some homotopy theory, but we should impose some relations. And that's the relations coming from the equivariant Nisnevich topology. Open covers, equivariant open covers are a basic example, and A1 invariance. So we force all of these projections to be equivalences. And then lastly, we stabilize with respect to representation spheres. Well, we're in the motivic setting. Here, representation sphere means well, the following. So if V is a representation, then I'll use this notation for the associated representations here. This is nothing more than the Thom space construction V mod the punctured representation. And here, standard remark, it suffices to invert the regular representation sphere. Okay, good. A representation of G over S, so it's a G equivariant vector bundle over S. If S is spec of a field, it's just vector space with a linear action. Right, good. So let's say that we have one of these guys. Then its homotopy fixed points are given by a familiar formula. Here, this is this E bullet G. This is the usual construction that love and know. This just formally exists. So that's something you can do, but here's something that's maybe more interesting. Sorry about that. So I'll write blackboard bold EG for the following motivic G space. So to define a motivic G space, all I have to do is tell you what are maps to it. So this is going to be defined by the formula. So the space of maps from W to EG, so this is a smooth G scheme over S. There's two options. It's either a point or it's empty. It's a point if W has free action. And it's empty otherwise. Okay. So defined this way, the following is a proposition. So we can make sense out of taking a quotient, and if we quotient out by the G action, so this is now a motivic space over S. This is the geometric classifying space of G, say as introduced independently by Morel-Blavatsky and also Totaro. And so it's a bad idea to give me too many boards. Can never figure out what I'm doing. So this leads to the following obvious thing to do. So here is an improved, well, I claim an improved version of homotopy fixed points. And let's note that there exists a unique map from this simplicial version to this geometric version, and so one way to think about these motivic homotopy limit problems is consideration. So X is a G spectrum over S. So we consider the maps from the fixed point of X to this improved version of homotopy fixed points to this version that we love and know. So now the question is, how far are these from being equivalences? Well, maybe one question is, why would you care? And I guess phrased so generally, it's hard to care about this, just a general thing. It's particular examples you might care. But so a sort of guiding philosophy here is you can prove things about this guy. On the other hand, this guy is computable. You have a homotopy fixed point spectral sequence computing this guy. So you might hope to be able to relate these all enough to leverage these two properties. There's different ways that this can play out. I mean, that's not all, this map may be drastic, and it may just be this map that you're interested in. So in this first example, it's really this first map that we're looking at. So this is joint with Thomas Gregerson, Jonas Kuhling, John Rognus, and Paul Arne Ostfer. Let's see, we're over a field K. Characteristic is not 2. And there's a technical condition here, finitely many square classes. The statement is that, and I'll write S for the sphere spectrum. In the C2 equivariant stable motivic homotopy category over K. The theorem is that if we take the fixed points complete it to eta and take the this sort of improved version of homotopy fixed points. Also complete at 2 eta. We have an isomorphism on homotopy groups. So this is sort of motivic Siegel conjecture. In the case G is C2. And let's see, example 2. So let's see. Let me tell the story this way. So so the following that I'm going to write down is basically a distillation of discussions with let's see, Agnes, Oliver, Vesna, and Paul Arne. Sorry, I want to say one thing before that. So there's a spectrum which I'll write like this in here, which represents real algebraic K-theory. It has the property that if you take its fixed points, you have the spectrum that motivic spectrum, which is often denoted KO. Some people denote it KQ. And if you forget, let's put that in quotation marks. So if you forget the action, let's just say forget. So if we forget extra structure, what do we get? We get KGL, the spectrum KGL that equipped just with a C2 action given by psi minus 1, sending a vector bundle to its dual. Okay. So, right. So, here's something that can be proved. So S is just a base scheme, Noetherian base scheme with 2 invertible. So you can consider the map from this spectrum KO to these homotopy fixed points. And this is an equivalence. And you can look at the cone of the map from this version of homotopy fixed points to the simplicial version. And you can show that this cone is eta periodic. Eta acts invertibly on it. And so, as an immediate corollary, you get that these are equivalent spectra. This isn't new, so if we take this and two complete, and if S is spec of a field, say finite VCD, this is the result of Hooprish-Ormsby that I mentioned earlier in characteristic 0, and Barrick, Karoubi, Schlichting, Ostvar in characteristic greater than 2. So integrally, still with S spec of a field finite VCD. This was a recent result of Oliver, Marcus, and Paul Arne. So their arguments, so this was analysis of slices. So this was the slice technique. And lastly, so recently Drew Herds put out a preprint that contains this as a corollary to sort of consideration of module categories. Over, I guess, KO and KGL and comparing them. Okay. Good. How am I for time? Interesting. Okay. So that's those are the statements. So the moral that I hope to convey is that you already know the strategies for proving all of these results. The nice thing, so the advertisement here for this sort of construction is the strategies for proving these results tends to be well informed from topological intuition. So let's take a look at details will differ. So let's take a look at maybe this part A of example 2. So the first thing that you think is that this thing is a limit of punctured sign representations, and it is. And so introducing the standard notation, this space by the co-fiber sequence. Okay, I put a base point there. Maybe there should be a base point there. This is an infinite sign representation sphere. And so for part A, what you got to do, you got to see that this spectrum is contractible. Well, what is this? This is the limit T n sigma mapping to KR and then taking the fixed points and unraveling what this is. You see that it suffices to show that this element of the motivic homotopy groups of the spheres, equivalent motivic homotopy groups of the spheres, that this element, let's call this B sigma, acts nilpotently on KR. In the topological case, when you prove this, this is exactly what you need to do. And unwinding things, you find that the topological analog of this is acting nilpotently on Atiyah's real K theory because it's acting by, I guess, minus eta, and eta is nilpotent. That doesn't work here, but nonetheless, this element is nilpotent here. This boils down to computation in the Grothendieck-Witt, higher Grothendieck-Witt groups, and relating those in turn to higher Witt groups, and then a base change argument, where you have some vanishing of the higher Witt groups over Z adjoin 1/2. But let's leave it at it does. Let me not say there's anything about this. And let me move on to outline of this motivic Siegel conjecture. I think I forgot to say it explicitly. I should have said it explicitly here that this is work in progress. We're working on writing it up. I think that this is all okay, but it's work in progress. So again, keeping with this philosophy that working with these guys, topological strategy informs, or topological intuition informs strategy. This is going to follow a familiar strategy. The first step is establish a homotopy pushout. So we have the fixed points of the equivariant sphere spectrum. We have these this version of the geometric fixed points. We have the, let me decorate these spheres with Ks, just to remind us that we're over a base field. We have the sphere spectrum over K, and we have this inverse limit, and I guess let me keep the notation in my notes. It's inverse limit of, so here, this is a lens space, so this is BC2, that's the geometric classifying space of C2, and this is a Tom spectrum of a virtual vector bundle over BC2. So this is established with appropriate versions of familiar Tate diagram techniques. So since this is a push-out, to analyze this map, suffices to analyze this map. For each n, we have, so we can understand the homotopy groups of the 2 eta completion of each of these guys via motivic atom spectral sequence. this whole thing can be understood via an inverse limit of motivic Adams spectral sequences. And so I threw in this funny technical condition of having finitely many square classes. The reason for that is to pull off this crazy maneuver. This is so k finitely many square classes that k has finitely many square classes. That in turn tells us that the coefficient ring of the mod 2 motivic cohomology is finite dimensional in every degree and Noetherian. And that's just enough for certain inverse limits to be exact and to make this work. So for each n, so we have the motivic Adams spectral sequence. So going x over the motivic Steenrod algebra. I guess I'll write it like this. So this is going to be mod 2 motivic cohomology. This is the coefficients. This is converging to the homotopy groups of the 2 eta completion of this guy. I don't remember whether or not I initialized this notation. That's just the homotopy groups. And so you can form the inverse limit of these spectral sequences to get a spectral sequence that looks like this. So this is x over the motivic Steenrod algebra. This is the continuous motivic cohomology of this inverse limit. And I have just enough room for its target. Okay, good. And what was that point B? So point C. So let's see, Gregerson's thesis is a motivic version of the Singer construction. So this is a functor. And basically have almost no time, so let me just tell you what's relevant about this functor. So this is an endofunctor on modules over the motivic Steenrod algebra. It has the property that there's a map going like that, which is a Tor equivalence. So he computed what happens if you stick in M2 and what happens is you get out the motivic cohomology of BC2 with a certain class inverted, also shifted. So here Y is the Euler class of the line bundle on BC2 coming from the sign representation. And well, that's nice because the whole reason for having done this was this has a nice geometric description, and now that description, it's not so hard to compute that the continuous cohomology of that L infinity minus infinity is exactly that. And good, so now we conclude by, excellent, I left myself just not enough room. Now we conclude so we start off with the motivic atom spectral sequence for the homotopy groups of the sphere. On the other hand, we have the motivic homotopy groups of the Singer construction applied to M2, which we just saw are the, well, we just saw, it's right there. This is convergent, so this is the inverse limit motivic atom spectral sequence, and this is converging to the homotopy groups of this thing. Thomas proved that this is an isomorphism there. So we conclude that that's an isomorphism there, which is what we wanted. And so that's the end of that argument. And I'm basically out of time, so let me conclude by saying happy birthday. Not to all of you, just to Doug.